Please welcome Neal Kruis.
Thanks, Elise. That was a dreamy introduction. I appreciate it. All right, so today I'm going to be talking about the future of heat pump water heater modeling. And just so everyone is on the same page, this is a heat pump water heater. This is an integrated heat pump water heater. There are really two kinds of heat pump water heaters that we're going to be talking about, but mostly on the integrated side. These are also called consumer products or residential systems. And basically you have a refrigeration system on top here, and above the tank, which is a typical part. And you can see the blower, compressor, evaporator, and then the refrigerant line comes down, and the condenser part of the refrigerant system wraps around the tank near the bottom. Hot water comes in at the bottom, is drawn out or cold water comes in at the bottom, and hot water is drawn out the top of this system. The other type is an external heat pump water heater, and these are also called split systems or central systems, and the components are sold separately. So you have a tank and then basically an air-to-water heat pump that draws. It actually has a pump built into it often, and it draws water from the bottom of the tank, runs it across a condenser, and then spits it back out at the top of the tank, kind of pushing hot water down into the tank as you draw. It's not showing up. This is a different system than I'm used to. Okay, I will try to do that. Sorry about that. Okay, so if we're going to model these systems, what kind of data do we need? What kind of performance parameters do we need? And what data sources exist to establish those parameters? So the first one that we often think of is the AHRI certificate or the directory. And like most systems, we have what in this system is called a uniform energy factor, which is kind of the miles per gallon for any water heater. But for reasons I'll get into later, this can't really be used to predict the performance of the water heater. The next piece of valuable data here is the rated storage volume. And you'll notice that above that, we have a nominal volume. Quick question here, who knows how many gallons of water a 50-gallon water heater can hold? I bet Jim knows. How many? There you go. Because volume is very hard to measure, folks. It's just, yeah, no, there's some allowances there, and so we need to be careful that if you're modeling a water heater, you're using the right volume and not the volume that you see on the product when you buy it off the shelf. Let's see. Yeah, I think that's it for this slide. These notes are a little small here. Okay. Okay. The next source of data is the product literature. And sometimes there's useful information here. We get dimensions of the product, but these are far from standard, and so they can't necessarily be relied on to be a reliable source of data that we might need to model these equipment. The third source of data is standard test data. And we have two sources, two organizations that standardize tests for water heaters. The first is found in Appendix E to Subpart B of Part 430 of Chapter D of Chapter 2 of Title 10 of the Code of Federal Regulations. If you want to read it, that's how you find it. And there's actually 4 tests that this describes. The first one is the first hour rating test, which is basically a measurement of how much hot water can your water heater produce in 1 hour without going below a certain temperature. The second set of tests are all called 24-hour tests. We have the standard UEF test, which is done at an ambient temperature of 67.5 degrees. But then there's some optional ones, which are particularly important for heat pump water heaters at 50 degrees and 95 degrees. And then the second source of standard test data is NEA, the Northwest Energy Efficiency Alliance, Advanced Water Heating Standards. And they have a test called the High Volume Draw Test, which is an 18-hour test. And all of these tests here are characterized by sampling data at 1-minute intervals or higher. So just to give you an example of what this looks like, I'm going to show a lot of plots like this. Just so I want to get you familiar with the layout. We have on the top, we have power input. In the middle, we have the flow rate, so you can see individual draws happening here. And then on the bottom, we see the temperatures inside the tank. They do these tests with, they take the anode rod out of the water heater, and they put in a rod with thermocouples attached to it at 6 equally spaced heights. And yeah, so you can see that, at the bottom of the tank, we have this gold line here. And as you draw water out of the tank, you get cold water coming in the bottom, and you can see that cold water kind of moving up during each draw, and eventually getting to higher thermocouples in the tank. And at some point, there's a thermostat that triggers the compressor to turn on, and you can see the temperature inside the tank increase until the compressor turns off again. So hopefully that makes sense. So now I'm going to go into just taking you into the simulation itself and to explain how we capture all that behavior in the simulations. So we use a tool called HPWH Sim, which is a bit of a mouthful, so we just abbreviate it as HPWH Sim. And it's originally developed by Ecotope, but we, Bigg Ladder, took on the maintenance and development of this after some of their programmers had left the company. This model divides the tank into multiple nodes. It includes parameters to characterize just the insulation around the tank, the condenser where it's located and how the heat is distributed inside the tank, electric resistance heaters, and any number of extra heat sources can be specified. Let's see, what else here? And once all this is characterized, once the equipment is characterized, the simulation is driven by what the temperature in the environment is. That's where the tank is losing heat to, and also where the evaporator is drawing heat from, what the inlet mains temperature is, and what the draws are. And those are all parameters or variables determined by the simulation, the whole building simulation tool. Okay. We use the same tank model for external condenser models. And one of the biggest differences here is that the tank and the evaporator might be in different environments. You might have the actual heat pump system outside or in a garage separate from your tank. One other important characteristic of the way we are modeling these systems in the compliance software is that we use a resolution that is much finer grain resolution than most of our whole building energy model simulation tools are used to. So usually we use hourly, but you can see if you look at actual draws versus the hourly averages, you get a very different story. For example, if I were to take a 10-minute shower at 2 gallons per minute, that would be a very different scenario for the heat pump water heater is for if I took a 1-hour shower at 1/3 of a gallon per minute. And the big difference there is you're never going to trigger that backup resistance heat if you are simulating these at an hour-long time step. And this is really important for the state of California, where we're incentivizing long-term system costs, and we care about long-term system costs and peak cooling or peak power and all these things that go beyond just total energy. So that's a bit of background on the simulation model. The next step is to enumerate all the performance parameters that need to go into the heat pump water heater simulation and explain how we can determine them from the available data sources. So I'm going to start with the tank. We get the rated volume from the AHRI certificate. The diameter of the tank we can get from the product literature. And then the UA, which is the measurement of how conductive the tank is to the adjacent environment, we can get that from the 24-hour test. So I'm going to show you another one of these charts that's modified slightly because I'm showing just the average tank temperature here. And if we kind of focus on this period, you have a few draws first, and then the compressor's running, and then it shuts off after it brings it up to temperature. You have this period where there's no draws, and it's just slowly coasting. And so we can determine what the UA value is by how quickly the tank is losing heat. The next set is the thermostats themselves. Often tanks will have two thermostats kind of located along with the resistance heaters. And we don't actually necessarily know where they are from product literature, but I'm going to explain how we can figure it out from the test data as well. The next piece, and the biggest piece, is the performance parameters for the condenser and the compressor. So the power goes into the compressor at the top, and then the heat is added in the condenser in the tank. And like any other refrigerant system that we model here, we know that the actual performance is going to depend on what the temperatures are at the condenser and what the temperature is at the evaporator. So here is some experimental data that kind of illustrates this. We have capacities on the top here that are on the left axis, and then the power is on the bottom, and that's shown on the right axis. On the x-axis, we have increasing condenser temperature inside the tank. And then for each of these different colored lines, it's a different temperature for the environment around the evaporator. And so there's a few patterns here that I think are important to note. As general rules, the capacity and power are both going to increase at higher environment temperatures near the evaporator. The capacity is going to decrease as the condenser temperature increases, and the power is going to increase with condenser temperature, which means that your efficiencies are going to be a lot lower on this side than on this side. All right. So historically, the energy modeling, we would just look at this and try to fit a biquadratic curve with 10 decimals of precision and call it good. But I would argue that for something like this, we can probably characterize both of these just 4 simple points. It's fairly linear, and any non-linearities in there might be artifacts of the data, and might, there's just a lot of noise relative to the accuracy that we need. We're going to do the same thing for power. It's mostly linear, so we only really need 4 points to characterize it. So that tells us for both input power and heating capacity, but what about the other parameters here for the compressor and condenser? So again, we're going to look at the test data for the system. We're going to zoom in to where the compressor is turning on, and we're going to use this to find the location of the condenser, the location of the thermostat, and what the temperatures are where the compressor turns on and off. So you can see if you follow this line down from when the compressor turns on, it happens to be where this navy thermocouple drops below 70 degrees. So that tells us that the thermostat for the compressor is located near this navy thermocouple here. And then you can see also that the heat is added near the navy thermocouple because that is where the temperature is increasing the fastest. So that's it. Helps us identify. Now, the thermocouples don't necessarily align with where the thermostats are. In this case, it's maybe more coincidence, and it might actually be somewhere in between. But that's all part of the process that we are going to get into in a bit. And then you can see that the compressor turns off once that blue or that navy thermocouple rises back above 125 degrees. The heating capacity, whether the heating capacity is greater or smaller, will determine how quickly the temperature increases. So a faster increase would be a higher heating capacity. A shallower one would be a lower heating capacity. And then the input power, as I mentioned, at higher condenser temperatures, you can see the temperatures at the bottom of the tank are increasing here. You can see that the power is also increasing because of that dependency on temperature. Okay, so that gives us a pretty good idea of what's going on at the condenser, but what about the resistance elements? You may have noticed that the resistance elements never kicked on, and that's why we need the high volume draw test data, because in the UEF test and all the other tests that are the 24-hour tests, those are designed, the manufacturers design their equipment so that they never trigger resistance heat, because that would be a huge penalty for the UEF. And if we remember, the resistance heat is really what drives peak demand and where our biggest costs are going to occur for these systems. And so the UEF and the UEF tests don't tell us anything about that, one of the biggest penalties for these systems. So we need to look at the high volume draw test data to figure this out. And as the name suggests, these tests use a very high, a 3 gallon per minute draw, and it's on for several minutes. And you can actually see that the compressor tries to start, but the machine realizes pretty quickly that it's not able to keep up, and it has to turn on the resistance heat. And you can see the difference in efficiency, or in power draw, between the resistance heat and the compressor energy. If we kind of focus in here when that resistance heat kicks on, you can see that it kicks on when the pink thermocouple now, which is higher in the tank, when that drops below 100 degrees, that's when the system kind of goes into panic mode. Like, I'm not going to be able to keep up, and I need to turn on the resistance heat. And you can see, backing up a little bit here. You can see that the input power, because these are just simple electric resistance, they don't depend on temperature. So the input power is actually very easy to characterize, because it's simply the difference between when it's on and when it's off. Going back to looking at the temperatures inside the tank, you can tell that the resistance heat turns on when that pink thermocouple, higher in the tank, drops below 100 degrees. And then it turns off, again, when it rises above that 125 degree set point. Unlike the compressor and the condenser, the light blue line here, that's the one that's increasing the fastest. And so that's an indicator that is where that lower resistance is located inside the tank. And that gives us all the information that we need to determine kind of the performance under any situation for when these resistance heaters are going to kick in. It's pretty rare, actually, that the lower thermostat or the lower resistance heater is going to kick on. That's kind of like a last-ditch effort if the entire tank is depleted. So that's the resistance heat. And I've gone through all these parameters to set in our simulation model, but I haven't really explained how we go about determining what the actual values are. I've just shown you kind of the relationship that they have to the test in the tank. So I'm going to go into some input parameter calibration and talk a bit about the process that we have there. So for all of these tests, we have an E50 test, we have the UEF test here, and what we're trying to do is, first of all, the manufacturers will provide us with some of this data, and so we have their measured data, and then we run our simulations, and what we're trying to do is minimize the difference between the measured and simulated for both the power and the temperatures inside the tank. So here we're just showing the top and bottom of the tank, but the same would be true for all of those points in between. And this is a very large multivariate, multi-objective optimization function where we're trying to calibrate 18 parameters to match 40,000 points of data. If you look at all the minutes of data across all the tests and all of the power and all 6 thermocouples, that's kind of the scale of the problem that we're trying to solve. And historically, this has been a very manual and kind of lengthy, time-consuming process of mostly kind of eyeballing things, because developing the code to automate this is a challenge. And so there's been a lot of kind of like fudge factors that have been added to this historically, and eventually get to a point where the results actually look pretty good, and we're confident that this actually represents the exact piece of equipment that that's being modeled. But as I said, this is a very manual process, and it takes time, and so there's a lot of challenges associated with this. And as a result, you might have a CBEC release, and then the manufacturer will release a new product after that CBEC release. And then we get the data from the manufacturer, we perform our calibration process, it takes us some time, and by the time we're actually done with that, it might be past another CBEC release. And this is exactly what Mike was saying in the conversation yesterday, the challenges that we have. So they don't actually get into the software until the subsequent release. And so the whole process is fairly problematic. On top of that, we don't, for each of these products, we have to put all these parameters into the C++ of the simulation engine and ship it out with the release, which makes it a little harder to manipulate. And so this is a slow process for the manufacturers. It's slow for the compliance analysts that might want to model newer equipment. And it's expensive for the CEC. And ultimately, it's just not a sustainable solution. So what might this look like in the future, in the distant future, in the year 2026, if you can imagine? If you're anything like the late, great Brian Wilson, you might be thinking, well, wouldn't it be nice if instead of trying to pull together all of these performance parameters and the lengthy and arduous calibration process, there was a single source of data that could be provided by the manufacturer to characterize all of this performance data. And fortunately, ASHRAE Standard 205 has already paved the path for exactly this purpose. So you maybe have heard me plug ASHRAE 205 before, and I do really think that it's going to be a very powerful approach to not just heat pump water heaters, but other equipment moving forward. And so what we've done is we've developed now ASHRAE 205 inspired representation specifications, which it's kind of a fancy word just for data schema, excuse me. And so we've done this for both integrated water heaters, which kind of encompass the tank, the resistance heat sources, the condenser heat sources, and for the central systems, separate representations for the air-to-water heat pump and the tank. And the tank here and the tank here are actually the same schema for data because they're characterized in the same way, regardless of whether it's integrated or not. And then these data schema also include the performance maps for the condenser heat source and the air-to-water heat pump. So just to show, we've actually done this now for I think 110 different units, converting what was in the C++ source code into JSON 205 compliant JSON files. I'm not going to spend a whole lot of time going through all of these, but I just wanted to show this as a basic example of what we've completed. Because now that they're part of a machine-readable JSON format, we can programmatically modify the parameters in this file to calibrate these models. And so we're now working on developing an automated calibration process where we can break the problem now into 4 smaller calibrations. One, where we're calibrating all of these parameters using the 24-hour tests, just kind of matching the tank temperatures. And then another set, 24-hour tests matching power. A third with the high volume draw test data matching power. And then the final one where we're using the high volume draw test data to match tank temperatures. And this makes the whole problem mathematically a lot more tractable and simple to process. And so the vision here is that we will have a program where a manufacturer could upload or put in their results data for all of these tests and hit the calibrate button, and it would spit out one of these ASHRAE 205 performance files, performance maps and data files corresponding to that equipment that is calibrated to their test data. And the ultimate vision here is that these files then can be stored in a CEC product directory that is maintained separate and independent from the CBEC releases. And so that way, when a new product comes along, the manufacturer can share their data or put it into the process, the automatic calibration, produce that 205 file. The CEC can review that file and then add it to the product directory, and then analysts can sync their version of CBEC to upload the new or update it to include all the latest products before the next CBEC release. The manufacturer is happy because their products are immediately available for code compliance. The analysts are happy because they can properly evaluate the latest products that are available. The CEC is happy because they don't have to pay Big Ladder to fiddle around with numbers in C++ land for weeks on end. And the utilities are happy because these products are accurately characterizing what impact they will have on the grid and their impact on long-term system costs and peak demand. And if successful, this model could be used for other product categories in the future. But one of the biggest advantages of this approach is that manufacturers eventually take ownership of the data and the performance of their equipment and get more engaged with the modeling community. And I think it's great that we have Mike here, but I don't think there are a whole lot of other manufacturers in the room, and they really need to be part of this conversation in attending these CalBEM meetings. So the conclusions here, pretty much what I just said. Manufacturers don't have to wait as long. Compliance analysts have more options. Utilities are more confident that the models are reflecting the impact on the grid. And the CEC has one less expensive bottleneck. But we're not quite there yet. There's still some next steps. These next steps include finding future funding to help get us across the finish line. And there are two contexts here. One is the DOE support for the Asteroid 205 project is sadly kind of expected to mostly disappear with the new administration. And so what we want to do is engage the manufacturers with the 205 process, and that's what we had been doing with the DOE funding. And then the second part here is that the CEC has been patiently supporting this calibration process for a long time, which I demonstrated is not a very sustainable thing. So if we can just get it across that finish line, hopefully they won't have that obligation, and we can have a much more sustainable funding situation moving forward. Once we have this, we finish this fine-tuned automation calibration procedure, then we can really engage with the manufacturers and see, make sure that that works for them, and invite them to participate in design of this data model. Because this data model that we've developed is largely based on the code that was originally developed by Ecotope and has some things that are from the minds of kind of software engineers and not necessarily the people that work with the equipment from day to day. And then once we finally have that, we should probably go back through and recalibrate the existing products in the database because the calibration process will have improved. So that's what I have. And I think Jim Lutz is going to present on a related project that has coming up, and then we'll open it up for questions for everyone. So thank you.
So I'm Jim Lutz. I do a lot of hot water stuff and heat pump water heaters going way back. This is using sort of the simulation tools, not to see how good the building is, but to see how good the test procedure is, and representing how good it is at rating a water heater. So the DOE test procedure, and I thought Neal did a very good job of describing it. It's designed to there's the quote, energy efficiency during a representative average use cycle or period of use, the key variables, and so the water and air temperatures, and then the draw patterns. So these are the draw patterns that are in there. What Neal didn't say is you get a different draw pattern. There's 4 different draw patterns. You have to test your water heater on a different draw pattern depending on what its first hour rating is. And that's because to capture the water use, how heavy the use is. The first hour rating is also used in the plumbing code to say what first hour rating you need to put into a building depends on the number of bedrooms and the number of bathrooms, not the number of people, even though it's the number of people that use hot water, but you don't know the number of people that are going to be in the building. The next thing is the air temperatures, and I still haven't figured out who actually said it first, but the test procedure is not your climate, it's not your building, and it's not your occupants. So is it anywhere close? And that's what we're trying to do. And NREL, the res stock tool, is really good at generating hundreds of thousands, or probably could do as many as you want, virtual simulated buildings with simulated people, and it's very representative, has all that. It uses Energy Plus. So what we want to do is generate a representative sample of buildings across the whole country, because the DOE test procedure supposed to represent the whole country. Run it, put virtual people in all those virtual houses, have them use virtual water heaters and virtual hot water, and see if the efficiency of different water heaters, different models like an A.O. Smith, a Rheem, different size tanks in different locations in the house, if that gives, the average of that gives you a number that's reasonably close to the UEF and is in the same order, so water heater A is always better than water heater B. Unfortunately, Energy Plus doesn't have a really good capability of doing the fine, small time steps that you really want to see when you're doing a simulation of a heat pump water heater. CSE, which is the engine behind CBAC Res, has that capability, has most of the models that Neal was talking already in it, so that'd be great to use, but we're still trying to get how the buildings go from res stock into CSE, and then there's the problem that the UEF test procedure is not what you see in a house. Nobody ever runs their water heater at the UEF draw patterns. So we're going to come up with a process to simulate the variety of draw patterns to capture that. And that's basically it. And if Neal will come back up here, you probably have to answer more questions than I will.
Pump water heater has a button where I can switch between normal and efficiency. And I forget if it says resistance, it probably says like quiet mode. How do you accommodate for that? And that's the only question.
I think that's a question about compliance. I mean, if you want to, you can always model it the way you want to model it. But for compliance, we have to ensure that the hot water load is met, right? And so in the compliance software for residential, even if you were to choose that, efficiency mode. Yeah. And you're not meeting the desired temperatures, the compliance software will add a penalty electric resistance to bring it up to temperature. And so whether you're using the resistance or not in your home, that's really a homeowner decision. But for the compliance process, we need to make sure if you can do it all with compressor, that's great, and you'll get points, and the products will get points. The more that they can rely on the compressor than the resistance heat.
So your model would be able to model either mode?
Yeah. It's like if you wanted to just model in the engine, you could say just basically disable the resistance heaters. And if you wanted to see like how bad of, like, what's the coldest water you get out, you could look at that as well.
No. There's another point to it. The manufacturer has to ship it in the mode they tested it under, in the box. And, you know, I don't know how many, probably 95, 99% of water heaters are installed just as they come out of the box. So,
Eric Holder up here in the back of the room. I understand that you would be calibrating these models with the sort of high resolution 1 minute data so that you could capture the electric resistance element behavior. When you then use those models in the compliance software, are you capturing that electric resistance behavior, or is it on a different draw pattern that doesn't then trigger?
Well, they are different draw patterns, but they're draw patterns based on real occupant behavior, and they're broken down into minutes. So we're still capturing that level of resolution in the compliance software, but the draw profiles themselves are going to be different. But they do have showers. They have long showers. They're pulled from a large data set of homes in California from real draws. So they include, you know, teenagers and all the other big water users. So, yeah.
2 questions. First one should be easy. Neal, you showed 12 nodes on the tank, I think just graphically, and then 6 thermocouples. Do you have a minimum recommended number of nodes for the model to get good results?
I don't think we have, in this compliance software, we don't have any that are less than 12.
Oh, really?
And historically, they've been multiples of 12 because of the 6 thermocouples that they're matching to, but we've since relaxed that. So, but for like compliance simulations, we don't want that to be user input that people can change or game because of it would just change the accuracy rather.
Gotcha.
Yeah.
Okay, and another quick one. Yeah, I really sympathize with the gentleman yesterday who talked about this delay. So honestly, I love your vision for how you see this panning out. So from the 205 perspective, is it then incumbent upon the third-party vendors to build some form of API that will call that data live? So as soon as the water heater vendors publish data, we theoretically could get it the same day and put it into compliance software?
I mean, that would be part of my vision,
Okay.
is that central repository, and there would have to be some,
Checks.
you know, some checks to make sure that people aren't modifying the data to game, right?
Got it.
But yeah, like some checksum to say, yeah, you're actually using the right file. So that directory would be available to CBEC, but also any third party.
Awesome. Yeah, I mean, just to validate the vision, that's exactly what was presented to us for fenestrations with IGDB. They have their database, it's on this cloud platform, and if you want to build an API to call it, you can, and that has happened. So I think it's proving your vision that, like, if this happens, I think vendors will rally around it. So thanks.
Neal, thank you. That was a great presentation. I think you really nailed on a lot of the challenges we are feeling as manufacturers. So, you know, kudos to you for all the work you've done on that. You know, again, the devil's going to be in the details. You know, I think this is a very promising approach. You know, manufacturers are obviously going to, you know, put this under the microscope from, you know, data privacy concerns and, you know, confidential information and all that good stuff. But I think this is a very good start. I think this is something we can certainly work towards as an industry, you know, moving forward to make CBEC a much more useful tool and, you know, get better data out there and kind of suit our needs and, you know, allow us to be able to sell the product as soon as it's actually launched to the overall market. You know, on top of that, like I mentioned yesterday, I think we do still need something from the Energy Commission to allow for equivalent products to kind of compensate for the current shortfalls of CBEC. But, you know, again, I think we're moving in the right direction here, and, you know, great work to you guys. Thank you.
Yeah, thanks, Mike. And I want to touch on the data privacy thing because that's a challenge that we are always facing with 205 in general, and I think well, maybe it's best for a follow-up, but there have been a lot of discussions about data security, data basically validating that the data hasn't changed, making sure that basically manufacturers have control over who receives their data and in what format and what they can do with it. So.
Hi, Jim. Clarifying question. You said that you're looking at data from real-world applications, and is that work in progress? And when can we see results from that?
It's field data for hot water use, and that's surprisingly rare and hard to get because it's harder to measure hot water use than, say, electricity use or air temperatures. So the data set that Neal used was from 2010, 2011, and it was from 100 homes where the flow rate of hot water was measured at 10-second intervals. And at that fast a data sampling rate, you can identify the end use by the shape of the draw pattern. A shower looks different than a sink draw, looks different than a bathtub, filling a bathtub, for instance. And that came from a residential end use of water study that was done by Aquacraft for, I guess, the Water Research Foundation. So it's a water utility sort of interest. And I had managed to talk them into doing, they did 1,000 houses. I talked them into adding an extra water meter and doing 100 houses at water heater. There is no similar data set completely comparable. There's a company called Flume that it's collecting 5-second water data at the house water meter. And they do the same sort of draw pattern recognition so you can identify, oh, that's a shower, that's a toilet, that's outdoor irrigation, that's a sink. How much of that sink water is hot and how much is cold, you don't know. A shower, you got a good idea because people tend to shower at 105 plus or minus. So and they have 300,000, couple 100,000 of these out in the field, but they're self-selected, they're not randomly selected. It's people who are really into their water use or they've been funded by water utilities. So we're going to get that data, but then we have to, or a subset of that data, and then we have to back out of it the hot water draws and what fraction of hot water of that draw is hot. So the draw patterns in CBEC are based on field data, but it's old field data that we had to do a lot of manipulation to account for new standards on clothes washers and dishwashers and shower heads and all that sort of stuff. So it's data, but it needs a lot of handling to get it in the proper shape.
Got it. One quick follow-up, is that okay? There's an equation in the ACM with which you can estimate the hot water draw for a home, and it takes two inputs: square footage of the home and number of bedrooms, right? And then there's one more that I saw in the sort of NREL outputs, which is only based on square footage. We've preferred using the one which has both two inputs rather than one input. Do you have any idea of which one's more accurate and what should be the right?
Well, there's two questions there. Okay. One is, what are you going to use for compliance? And the other is, what are we going to use on our project to see if the test procedure is right? So, and it's not the square footage of a house that uses hot water. It's the occupants, and it's the occupants' behavior. And I can tell you from looking at hundreds of houses worth of water use data and hot water use data, it's even crazier than, you know, air temperature or, you know, space temperature. It depends on who the people are and their lifestyle. You know, a single older person living by themselves uses much less water than a family with 4 teenagers, and yes, teenagers do use more hot water, or at least American ones. You know, so it varies, and it doesn't vary just between house to house to house, or family to family to family. It also varies from day to day to day, and dramatically. Like, you know, even if everybody's home, some days they'll use 3 times as much hot water as other days. So I don't know if that helps or not.
Perhaps it's time to look at those equations again, because you know, with all the data that you have access to now, that you guys have been looking at, maybe there's a tweak that's needed on those equations. Maybe
Yeah,
that can come out.
with the equations are intended, because I know I'm familiar with a number of the equations. There's ones that try to estimate like how much losses you have just because fixtures are far away from the water heater, things like that. But this is to estimate
The draw. How much hot water draw there would be for a home.
Yeah, I think, I don't know if that's simple enough for equation, because and I don't yeah, I guess what's in the ACM is not what's done in the compliance software, at least, because that's actually a much you know, it's the statistical based with very stochastic behavior. So yeah.
Okay, thank you.
Yeah. Yeah.
Double trouble, yay. All right, that brings us to our final break. It is just a quick stretch your legs, 15 minutes, because after that, we're gonna do my favorite part, which is recognizing folks in the industry, in the community, who have been instrumental in meeting these carbon reduction goals and energy efficiency goals. So please take a quick stretch and a bend, and then come back here at 2:30 sharp.